provide a path for the robot to follow, the algorithm team chose the A-star algorithm to search for the shortest path, using Euclidean distance for heuristic. Factoring physical limitations, we conceptualize a search graph with a maximum vertex degree of 6 for the possible actions that the robot can take. The action costs are reflected as weighted edges to indicate preferred actions.
To visualize our algorithm, we created a simulator modeling the actual 2x2 meter arena using a 20x20 grid and a 3x3 square for the robot. We can manually set the obstacle or preload it using CSV file. To aid in testing different arena setups, we can also export the current setup into a CSV file to be used later. With this, we are able to test and run our algorithm before the robot is physically ready.
Hi, Arjun here from the STM team. The STM's role is to ensure that the robot moves accurately for both straight lines and turns while following the parameters given by our algorithm. To maintain this accuracy, we use a PID algorithm. This algorithm takes in the encoder values from the DC motors and uses a feedback loop that allows us to correct any deviation in the movement. For straight lines, we use a simple linear calibration to estimate distance, and for the second task, we receive ultrasonic readings from the RPI to stop in front of the obstacles. For turns, to maintain a sharper turning radius, we use a 3-point turn in both the forward and backwards direction. This, coupled with the PID, allows us to achieve accurate 90-degree turns.
We will now present our latest rover control system. First, click on the Bluetooth button. Only one device can be chosen to connect to. Now the control system is successfully connected to the rover. Generate obstacles. When there is a newly discovered obstacle, add it to the map and drag it to the targeted position. Click the obstacle to change its orientation. Curiosity is now generated. Use directional buttons to control rover movements.
For image recognition, 150 images were taken of each of the image faces, under different environmental and lighting conditions. The images were then labeled individually using Label IMG, a graphical image annotation tool. The images were uploaded onto RoboFlow, and data augmentation techniques, such as varying the levels of blur and brightness, were implemented, leading to a total of more than 4,100 images for the model. Finally, the images were processed using YOLO v5, where a test, train, and valid dataset were used to train a model with an MDP accuracy of 0.907. A server was hosted on the PC, and the ImageCMQ library was used to send pictures between the RPI and the PC for processing. Image processing was done on the PC rather than the RPI due to higher computing resources and faster speed.